Okay, we're good.
Hi all, we're the Intelligent Ground Vehicle project team. My name is Tony Ma. I'm the project lead.
Hi, I'm Cole Johnson. I'm a mechanical engineer on the team.
My name is Jack Gusson. I am the design mechanical engineer for chassis and suspension.
I'm Mike Kazarian, and I'm the drivetrain and steering team lead for the team.
So a little bit on our project. We're trying to create an intelligent ground vehicle that can navigate an outdoor obstacle course while maintaining a speed of 1 to 5 miles per hour. It's a competition held in Detroit, Michigan, held by the DARPA military company as well as the big car companies there. There's 4 components of the competition. There's the AutoNav part of the competition where we autonomously navigate over a course with potholes, barrels, trees, etc., and try to avoid them while trying to reach the end of the course. The interoperability challenge, where they have a UI interface and you try to connect remotely to your vehicle and put in a coordinate, and your vehicle moves to that position. There's also the design presentation that we have to give on our project, where we show all our design concepts and what we decided to do and our justifications. And then there's also the cybersecurity challenge, but we're not participating in that because we lack the manpower and knowledge to compete with that. For our goals and objectives, so we decided our goal is just to design an autonomous ground vehicle that can at least compete in the AutoNav and interoperability challenge of the IGBC competition. And so, and part of that, we would also compete in the design competition. So our objectives would be to maintain an average velocity of 1 to 5 miles per hour, dodge obstacles such as potholes, barrels, and trees, follow a laid out track, climb incline ramps, and move accordingly to location-specific movement commands. So this is our design criteria. We decided this based on IGBC rules, as well as numbers and facts we could clearly state that we knew would be part of our robot, and say that we could design according to these design criteria. This is our timeline. We decided that we would finish our design criteria by week 4 of fall quarter. And then we would also decide on the finalized design in week 7, which was last week, which we already have, and now we're working on finalizing a CAD design for our project.
Alright, so I'm going to talk to you guys a little bit about our project progress. So since we are a new 189 team, and since a lot of us are new to the senior design group, our first goal was to pick out some design criteria, which was shown in the earlier slide. So a lot of our initial work was a lot of mathematical analysis and some research to see what would work and what wouldn't work. And some of our design criteria are, turn radius, weight of the robot, how much torque our motors need, etc., etc. So we've successfully picked out the motor that we need, what steering mechanism we're using, what material we're using for the chassis, and what type of suspension we're using, and we've created a preliminary CAD model. And our current goals are to complete our CAD model and to run some SolidWorks simulations and analyses, and to test some of the sensors that we have, because we're going to be using ultrasonic sensors and some cameras as well. And our future goals are to begin manufacturing and to do more experimentation with our sensors. So for our steering, we used our initial knowledge of one of our previous classes, and so we initially began by researching 3 types of steering mechanisms which were familiar to us: Ackerman, one-wheel steering, and parallel steering. Ackerman is, from our experience, Ackerman is really accurate because the wheels turn at different radius to have a similar center, a turning center. Though the drawback of that is that it has a large turn radius, and for our purposes it wouldn't be feasible because we have to react a very small interval of time in order to avoid the obstacles. And so through some research and through looking at previous IGBC manuals, we realized that a differential steering mechanism would be the most feasible for our purposes, and it has been used before, so we do know that it's achievable. And so the thing with differential steering is that each wheel has its own motor, which allows for a very, very small turning radius. Essentially, if we wanted to, we could turn the robot in place by turning one wheel one way and the other wheel the other way. And we also picked out our our motors for our drivetrain. So we decided we picked out a 3-wheel chassis with 2 wheels in the front and 1 wheel in the back. The 2 wheels in the front are going to be the ones that are being driven by the motors, And so after running some calculations based on including the weight of the robot, the acceleration of the robot, what velocity you want, and the wheel size, we figured out that the required torque necessary for a 120-pound vehicle would be close to 32 foot-pounds of torque. But obviously this is an overestimate because we calculated it based on if we were going up an incline all the time, and we also overestimated the weight. So after thorough research of catalogs, we found a motor that would be able to supply 180 RPM and 20 Newton meters of torque, which translates to around 15 foot-pounds of torque. It's really difficult to find a motor with these specifications because we were limited on budget, because obviously to find a motor with high RPM and high torque requires a lot of money, and we were trying to limit our expenses as much as possible. But we were able to find a motor for our capabilities, and so we're going to have one motor on each wheel in the front, which combines to around 30 foot-pounds of torque, which should be sufficient for our purposes, because our estimates were about an average of 3 miles per hour, but obviously we can go anywhere between 1 and 5 miles an hour. Pass it off to Jack.
So basically the idea for our chassis is that we want to try to make it very simple, but also able to house all of our electronic equipment in a way that's able to keep the center of mass slightly front-loaded, but still near the center. So we decided on, for the start of the frame, to use inch by 1/8 inch aluminum piping, so that way we can start with a frame, lay out sort of a base model where we have some parts on the bottom, on the side, and then we can lay out a series of plywood planks, roughly 1/2 inch to 1 inch thick. So that way we could house all of our electronics, including motor controller, possibly the motors, the graphics that's going to be housing the camera equipment, as well as a PVC pipe that's meant to go up to 6 feet relative to the ground. Obviously, we're trying to make sure that the cost is beneficial to us, as we're pretty limited with that. So $2.10 per foot is really beneficial to us. This is kind of a suspension system that we've been working on. For the last couple of weeks, we've been thinking, do we want an independent or a non-independent suspension? Are we going to do a dead axle or a live axle? Is it going to be in the front or the back, depending on drive? We ended up that basically the front suspension is going to be sort of more of an independent suspension. Basically that the wheels would operate independently of each other or move vertically independent of each other. So basically the idea is that there is a series of connections to the wheel and a suspension spring that's going to basically lift up or compress as the wheel either goes over terrain or under terrain. And then for the rear suspension, we're going to be using a single caster wheel placed roughly along the Y center axis, assuming the plywood as our X and Y. And it's going to have a vibration isolator, so that way we can not only balance out the weight, but also reduce as much suspension as physically possible on the back wheels. So this is the entire preliminary CAD design. The idea is that bottom section is going to be our first plywood with all of our motor controllers, and we're also going to be supporting a 20-pound brake in there. So we're going to try to put it roughly -6.5 inches back to roughly 1 inch forward relative to its center of mass. So that way we can get a front loading of roughly between 0.75 to 2.5 inches on the overall design. There's going to be a roughly 50-inch PVC pipe that's going to be going on top of this section of the intelligent ground vehicle, which will be suspended via a second plywood sheet that's also going to be able to have some of the wiring and equipment running through it. And now we'll go ahead and
So for our control systems, we kind of went through a variety of options, including ultrasonic, LiDAR, radar, and cameras. Based on our pricing, what was realistic to us was really ultrasonic for near object avoidance, and cameras to see a little bit further. So as you can see, pricing is pretty dramatic for cameras and ultrasonic versus radar. As far as coding goes as well, it's a little bit easier. So we decided to go with those two. As far as our overall budget, this is the percentages we decided to devote to each portion of our project. So here's the rough estimate for that. And then our biggest issue right now is funding for transportation to the competition. So we're looking for maybe Europe funds and possibly sponsorships to solve that issue at the moment. And then another thing we have is our resources, being Dr. Rankensmeyer as our advisor. And then here are our team leads, including Tony, Ben, who's not available today, Mike here, and Daddy on controls. We're all taking 1 units this quarter, so it's a little slow, but we've definitely been able to keep up with schedule. So as far as our team structure, there's Ben, Daddy, and Brandon, who is not listed on the last slide, but he's sort of a volunteer, I think, on our team. Here's myself, Jad, and Tony as the lead. And if you have any questions, we can take those now. So.